Welcome to Shelly Physics, episode on impulse momentum and conservation of momentum law. This is part 2. We're mainly focused on the conservation of law here. And it's a law because it comes from Newton's second and third laws. And what this is great for is collisions and explosions. So we're going to have a collision we're talking about here, car collision. Everyone survives this collision. Everything's just fine. Works out in the end. So we got two cars. They're going to collide here in the middle. Now, like I said, second and third law happen here. So let's think about that third law first. There's going to be a collision. So there's a force that's going to be applied to car 1 and a force that's applied to car 2. So this is car 1 over here. Call it car 1. And call this one car or vehicle 2. You're going to have a collision. So how will that force on the first car compare to the force on the second car? Which one's going to be greater? The one with more mass? The one with less mass? Remember, Newton's third law says there's going to be an equal and opposite force. So force 1 is equal to force 2, but it is opposite. It's in the opposite direction. So that's Newton's third law here. Third law at work. Next, bring the second law in. Now this is where the impulse part happens again. We're going to use the impulse equation, that form of Newton's second law. So let's think about the force applied to vehicle 1. F1 is the force applied to vehicle 1. T is the time of the impact. And what's that going to do to the vehicle? It's going to change the vehicle's momentum. Mass 1, velocity 1 final, minus mass 2, velocity 2 final. Oops. Where am I going with that? My brain's going a little ahead of myself. So the change in momentum of the first car. Maybe I'll make that mistake for you. Don't make that one. I already did. Minus mass 1 times initial velocity. I'm going to keep it just as V1 so we don't have too many rogue subscripts. All right. Now what about this T? I just glossed over it. This is the time of impact, the impact time. So when that car's frame is crunching together with the other car frame, that's the time of impact. When everything settles down and the collision is over, the impact time is over also. So this would help us to think about the force on the first car in terms of its change in momentum. Well, what about the second car? It'll look very similar. Force on the second car times the time of impact. And notice I'm keeping it just T, not T1 and T2, just T. If the force of impact is the same, then the time of impact is the same. And that's what I'm referred to up here, the force of impact being the same. But in this one, if we look at its individual Newton's second law application, M2 times V2 final minus M2 V2 initial. Okay, so the F is the final conditions and the subscript numbers without the F is the initial. Notice mass stays the same in this case. You may think about rocketry. With rockets, it is ejecting mass, and there is a Newton's third law application there. So in that kind of situation, and using conservation of momentum law, the mass might be changing, and most likely if the rocket's ejecting its own mass. But in most situations in this class, we're going to have a mass that remains the same. So the mass stays the same, but the velocity has a final and initial value. All right, so these two together are applications of Newton's second law. So if both of those are true, let's apply the one to the other. What would F1 be in terms of everything else? Well, if we divide both sides by time, and divide both sides by time here, we'd have F1 in terms of its change in momentum and time, and F2 in terms of its change in momentum and time. Well, let's plug them up here at the top, Newton's third law. So instead of F1, we're going to substitute this creature in there. Let's not forget the negative. Bring it down a little bit. Negative all of that. We're going to plug in M1, V1 final, minus M1, V1, all over T. That's a bracket, equals F2. So negative F1 equals F2. And let's replace F2, force 2, with its M2 V2 final minus M2 V2 initial over time. All right, we got a time in the denominator of each side. Multiply both sides by t. That cancels that t out on both sides. And we're left with a negative that distributes negative m1 v1 final. Negative times a negative is a positive. Stand and deliver. And there's no negative to distribute on this side. Whoa, what is that? That is a bunch of momentum. That is right there, okay? There's a bunch of MVs. Well, if we look carefully at these, there's some terms with final amounts, and there's terms with initial amounts. Let's put the initial amounts on one side and the final amounts on the other. I'm more of a initial comes on the left side, so we're gonna keep that stuff over here to that left side. So we're gonna put add this final amount to both sides, algebraically move this over, and we're going to add the initial M2V2 to both sides with the purpose of moving that one over. So M2V2 cancels on this side, M1V1F cancels on this side, and what are we left with? Let's put these initial conditions together. M1V1 plus M2V2 equals M1V1 final plus M2V2 final. What insanity is this? This is initial momentum 1 plus initial momentum 2 equals, you guessed it, final momentum 1 plus final momentum 2. Remembering that P equals mv for momentum. All right, our final reflection. The initial momentum of the system is equal to the final momentum of the system. And I'll write that word in there. System. What we're seeing here is that momentum is always conserved. There's no like friction momentum. There's no heat loss momentum. Momentum is momentum. And momentum comes from an impulse. So unless there's an external force on the system, this momentum is going to stay the same within that system. Call two cars a system, momentum is going to be the same before a collision and after a collision within that system also. Well, besides collisions, what else can apply here? Isn't a collision kind of the opposite of an explosion? Yes, it is. Have you ever looked at the videos where something's like crashing and you expect it to like crumple and like stay all mangled and stuff like that, but then you reverse the video and it pops back to normal? It's kind of like in Doctor Strange when he like redid time and everybody like went back together and all the buildings started like popping back up. It's kind of like that. An explosion and a collision are opposites. But there are two kinds of collisions. There's an inelastic collision, and that's the kind of collision I was just talking about, where two things come together and kind of crumple and they stick together. That's an inelastic collision. And then there's an elastic collision. An elastic is like elastic rubber band, elastic bouncy ball, a bouncing kind of a collision. So let's say we've got an inelastic collision. That means mass 1 and mass 2, they're going to come together and they're going to stick. This is 1 and 2. All right? As opposed to a elastic collision. Here we're going to have mass 1 and mass 2. They're going to come together, but this time they're going to bounce. There's a spring-like mechanism, whatever's causing that bounce, they're going to spring back. It's the elasticity of the objects themselves. Could be an actual spring in the middle, but that's going to be a bounce. So there's a bounce there. All right, so what happens? What is the difference here? We're looking at initial momentum of the system equals final momentum of the system. So if we've got mass 1 having an initial velocity and mass 2 having its own initial velocity, afterward, mass 1 will have a final velocity and mass 2 will have a final velocity. All right, so that's the system here. If they bounce, it's going to look just like this. This is what the expression is. We have two separate objects before the collision. We've got two separate objects after the collision. They may have the same or different velocities as before, but they're obviously in different directions. At least the magnitude might be the same, but the direction is definitely different. So the velocities do change. Now, what if there's a sticking collision? Well, what's that mean about the final velocity of both objects? If two objects come together, they collide and lock up, they may just sit there at rest. Now that would happen if M1 is equal to M2. But imagine now, if they're coming together maybe at the same speed but opposite directions, but one is a bigger mass than the other. Bigger mass, smaller mass. What's going to happen then? Well, when they lock up, which one had more momentum? In which direction before the collision was there more momentum? Well, if, like I said, there was V1 had mass 1 had a greater value than mass 2, but they had the same velocity, opposite directions, we might have like a 10 plus a -5, and the -5 would come because V2 is in the opposite direction of V1. But if M1 is greater, then you might end up with a positive amount over here that's greater than a negative amount over here. So a 10 plus a -5 is a +5. The overall momentum of the system would be in the direction of M1. Therefore, afterwards, the final momentum of the system must be in the direction of M1. If they lock up, which way are they going to continue moving? In the direction of the bigger mass. Bigger masses mean they have a greater amount of inertia. And objects with more inertia tend to keep moving in the same direction more than objects with less inertia, less inertial mass. All in all, what's this mean? For an inelastic collision, V1 final is the same as V2 final. And we can just call them VF. All right. So this might be a conservation of momentum expression, especially if we have an elastic kind of collision. But what if it's inelastic? If we apply this concept that the final velocities are the same, they're locked up and they're moving together. One's not separate from the other. They have the same momentum. They're going to be moving together in the direction of the larger mass or the one with a greater momentum. You know, sometimes a smaller mass might have a much larger velocity than the larger mass. So that larger velocity could also give the smaller one a bigger momentum to start with. And the momentum of the system would then therefore be in that direction of that smaller mass. It's moving much faster. That's how in sports like football, that's how the smaller players can actually break through the larger players. They have to have speed, they have to have velocity to get past the larger players. Larger players don't have to have as much speed to overcome the small ones. Sometimes they can depend on their own mass, but sometimes they're all really big, fit athletes. They can all find a way to get through one another. That's what the game's about. Moving on, away from football. For the inelastic collision, they start out as separate objects, just like the elastic collision. But since they lock up, look what happens here. Instead of writing a V1 final, we're just going to write V final. This is the final velocity of the locked up system of two masses. They both have the same VF. What can we do with that? We can factor out a VF. And what's left? We could look at this in a slightly different way. By factoring out that VF, we're left with an M1 plus M2 VF. M1 plus M2 quantity times final velocity of that locked up object, that bigger object that's combined now. So if you look at this kind of expression, this is the total mass of the locked up objects. They're behaving as one single mass now, traveling with a velocity VF. So you can see that quality in the equation there. So that's for inelastic as well. So elastic collisions, inelastic collisions. And finally, explosions. With explosions, we have one big mass that later on breaks up into two smaller masses. From some kind of event, some kind of explosion type of thing. You know, people can explode. I'm not talking about like exploding people, that's kind of gross. But two people together can explode. Let's take two ice skaters. They're out on the ice and they push hands off of one another, and one goes one way, the other one goes the other. They're exploding away from each other. Objects that were together become two. So we don't need to have violent explosions, but this could be, that's an action arrow. Something happens here. Okay, action arrow. There we go. So one object becomes two. That's what we have here. So what would that expression look like? Well, we might have a big M times an initial velocity equals mv1 final plus m2 v2 final. One bigger mass breaks up into two smaller ones. But we can actually do with a little less information here. You see that right now there's three masses, but the big M compares to little m1 and little m2. So since the big M1 becomes, I'll put a little becomes arrow here, M1 plus M2, we could just say M1 plus M2 initial velocity equal M1 V1 final plus M2 V2 final. Now hold on a second. Notice this form is exactly the opposite of an inelastic collision. Here we had two objects, momentum coming together to make one combined massive object moving at a single final velocity. Well, with the explosion, we've got a combined massive object moving at a single velocity. The only difference is this is the initial velocity, breaking apart into two different ones. All right. So all in all, when you're handling a conservation of momentum situation, think about what's involved. There's the momentum of one object, momentum of a second one. Now, if it is an elastic collision, if they stay separate, then just conceptually in your head, just think, okay, we're going to have momentum of the two different objects. One might be going one way, one might be going the other. I don't know. They're going to be separate. That's an elastic collision. We might have an inelastic collision. Same kind of thing, except now it's momentum of both of them together. And finally, we might have an explosion. We might have a momentum of some object equals the momentum of its first piece plus the momentum of its second piece. Now, conceptually, once you have that in your head, then it's as easy as substituting mv for the rest of it, and you just keep the subscripts going right. Okay. P1 turns into M1 V1. P2 turns into a M2 V2. P1 final is a M1 V1 final. P2 final is a M2 V2 final. It's a real easy thing that we don't have to worry about kinetic momentum or gravitational potential momentum. No, it's just momentum is momentum. Later on, the only other kind we ever see is angular momentum, but that deals with rotation. We'll get to that later. This unit, there's only one flavor, MV. What about the inelastic? So this would be our elastic. Let's get that recorded here. What about the inelastic collision? P1 would turn to an M1 V1. P2 M2 V2. Now momentum of both, They're going to combine into a single m1 plus m2, and they'll be moving along at the same final velocity at the end. This is how it transforms from your head, thinking about the objects, thinking about the collision, into a workable equation form where you can plug in values and solve. What about an explosion? This might look like something to memorize now. It's not. It's completely not something to memorize. We're just dealing with P's translating into MVs. An initial momentum. It might be two different pieces. You know what? Maybe if it's an object that breaks in half, you might say m plus m is the original mass of this object. And it breaks up into two equal amounts. mv1 final plus mv2 final. That signifies that both pieces have the same exact mass. Maybe this is a rocket that breaks up into two pieces of equal mass. And they go exploding apart. M and M. Okay? That's what it could be as well. Let's see something in action here. Here's our problem, and we're going to need a calculator. All right, car and a truck collide head-on in an elastic collision. A 1,000-kilogram car was traveling at a velocity of 15 to the right before the collision. A 2,500-kilogram truck is traveling at a velocity of 12 meters per second to the left before the collision. And then after the collision, bam, the truck is still moving left, but at a speed of 2. Notice there's a emphasis on direction here. We need to remember in this problem that momentum is a vector. It's not like energy where 1/2 mv squared, where if you got a negative velocity, it goes away. All right, energy is a scalar value, but momentum is a vector value. That's what we have to remember here. So negative momenta is in the opposite direction as a positive momentum. All right, so let's keep that in mind. Determine the car's final velocity after the collision. That's our target. All right, so where do we start? Oh, we could get jumbled up and confused with all these numbers flying this way and that, but you know what? The place to start is not with the numbers, it's with one simple statement. All the physics can be done just by reading that first sentence. A car and a truck collide head-on in an elastic collision. It means they're going to bounce, but if they're colliding, there's a car and a truck. The only thing we need to start with is this major concept. The initial momentum of the system is equal to the final momentum of the system. Then our next step, we can take this one piece at a time. What makes up the system? A car and a truck. Those are our two objects. Momentum of the car plus momentum of the truck equals the final momentum of the car plus the final momentum of the truck. Do you need to do this every single time when you solve these problems? No, but I really encourage you, the first few times you're doing these problems until you get used to it, this is what the start of every problem is when there's a collision or an explosion. Conservation of momentum. This is where the equal sign is going to come from. In an equality to solve for an unknown. So, get this into your head to start with. What is my system made up of? A car and a truck. Before and after. And now you're ready to plug in your P. Every P gets an MV. So this P gets an MV. This P gets an MV. MVs for everybody. Thank you, Oprah. So anyway, Oprah Winfrey used to do this thing in one of her shows, in her TV shows. You get a car. Everybody gets a car. Okay, anyway. Just remind me of that. It's a family joke. Anyhow, every moment of the car gets a mass of the car, velocity of the car. Moment of the truck is mass of the truck, velocity of the truck. And then we got these final conditions. Mass car, velocity car final, plus mass truck, velocity truck final. And now we're ready for the numbers. You see, don't worry about the numbers. If you get a problem with a whole bunch of numbers ever, see if you can, write something out first before you worry about the numbers. Now we're ready to plug them in here. Or plunk them in. Yeah, way to go, Shirley. So the mass of the car is 1,000. The velocity of the car is 15 meters per second. Mass of the truck, 2,500. Velocity of the truck. Oh, now we got to be careful here. So this is where the directions come in. If I'm saying right is positive, because this is a positive 15, I'm going to make a little indicator here. Right is positive. So that means this 12 meters per second is, as it's to the left, we're going to make that a negative. That's how it looks. Now we got the mass of the car again. It didn't change. And velocity of the car final, what is that? Oh yeah, that's our target. Let's never lose sight of our target. Write it out here so you always got in mind. This is what we're looking for. And the mass of the truck, 2,500 again. And its final velocity is 2 meters per second, also to the left. It's in the same direction as its original speed. It's also a negative, but now it's 2. It's slowed down and it hit something. It's moving a lot slower now, but still in the same direction as before. All right, now it's just an algebra problem. Okay, the physics came with the thinking of conservation momentum. We substituted in the MVs. This is great news. We don't have to worry about potential momentum. We don't have to worry about kinetic momentum or elastic potential moment. No, it's just one kind of momentum, MV. The only other kind you'll ever run into is angular momentum, but that's when things are spinning. All right, these cars are not flipping over themselves. You know, they have spinning wheels. That's not important here. The centers of mass of these cars are moving. That is what we're worried about. There's only one momentum, MV. Let's solve it. 15,000. This is times 12. Is that 30,000? It is. I wanted to say 30,000. It wasn't. Coming to the tip of my tongue. This is 1,000 VCF. And then negative 5,000. We got negative 15 G's over here. Add 5,000 to both sides. That gives us a negative 10,000. And perfect. Final velocity of the car is negative 10 meters per second. How should we write that? 10 meters per second left. Speed and direction. So, does this make sense? Did the car go through the truck? No, thankfully it didn't. The truck is going at a negative 2 meters per second after the collision. The car is negative 10. So it went from a 15 to the right to negative 10 to the left. This is not realistic. First off, I just gave an arbitrary final velocity. But if you do notice, the overall speed of these vehicles is decreasing. So the kinetic energy has decreased. There's been some energy absorbed by these vehicles. And this is why a smaller car, when hit by a larger truck, can go spinning off the road. So you got to be careful about speed when you're on those highways going quickly. However, the overall impact would probably absorb more of this energy, so this car wouldn't be flying off the road so fast. But in this case, with what I have here, 15 to the right to negative 10 to the left is our overall result here. So I hope this has been a little helpful, at least, but even more helpful when you get started. Attached to this video, if you look in the notes, is a great worksheet for, it's called Gaining Momentum. It's for getting used to using these expressions. What I went over here is something close to the example on that one. But on the front side, you can take these first two lines, start it up by putting this momentum of the car and the truck. Think about the momentum of each piece before replacing it with those MVs. And that way you're going to get the physics first and everything else will fall into place. Hope this is helpful.